Hello. In this video, we are going to go through some instructions that need to be followed when you need to use the generating engineering demand parameters using the multi-degree of freedom shear model or using the FEMA P58 simplified analysis method as a way of defining the structure response data. In order to use these options, first you will need, of course, OpenSEES to be available on your PC machine. So after the installation of EaRL, you need to go to the installation directory. This would be by default inside the C drive, in Program Files, University of Southampton, EaRL, and go inside the application folder. So right here, these are all the files that has been installed automatically or generated automatically when EaRL was installed. Right here you have the EaRL executable, which during the installation procedure we also added a shortcut for it on the desktop. So in the same time, there is an OpenSEES executable that has been generated by EaRL during the installation process. The user need to make sure that OpenSEES is actually working inside this directory. So if I double click on the OpenSEES executable, so it seems that it's opening without any problems. There are no errors here, and OpenSEES is ready to run. So this means that OpenSEES has been installed correctly on the machine. Of course, this is the case here because before I did the installation for EaRL, I already had the Tickle source files as downloaded from the OpenSEES Berkeley website or web page. So I downloaded these files online and then I installed them on my local computer. And now after I installed EaRL, so I can see that OpenSEES is now working, which means that if I utilize the features in EaRL that is running a multi-degree of freedom shear model or using the FEMA P58 methodology, then it should work fine without any issues. Other files that has been generated during the EaRL installation include some Tickle files that are necessary for running the multi-degree of freedom shear model. So now in order to do this, in order to run these options, you will need to open EaRL actually not from the shortcut. This will need to be done through the actual executable inside the main directory. So I will open EaRL through this executable, but in the same time I will need to run EaRL as administrator on my PC. So these are the two main instructions that need to be followed in order for these features to work. You will need to open EaRL from the installation directory on the C drive, and you will need to run it as an administrator. The reason for that is that once EaRL starts running OpenSEES, it will need to write some result files and text data inside this directory. And if you don't have a permission to write on this directory, which is typically on the C drive, then this will cause a problem in running OpenSEES or saving the data. So this is why it needs to be ran as an administrator. The second thing is that you need to open EaRL actually from inside the directory, sorry. This is because once EaRL opens, it saves the directory where the executable is located. And this is important because this directory already have all the subroutines and the tickle files and the OpenSEES executable that are necessary to run the multi-degree of freedom OpenSEES models. If you open EaRL from the desktop, then the main directory will be the one on your desktop based on the shortcut, and this of course will cause some errors later on. So now that EaRL is open, the next step would be to start a new project and define the response data for using any of the two options, the FEMA P58 simplified analysis method or the multi-degree of freedom nonlinear shear model. For this demonstration here, I will just open an existing template project and start from it. So I'll just browse to the location on the desktop. And from previous videos, we were defining like a multi-stripe analysis. So now I will modify this response data, and I will define or generate structure response data based on option number 5 over here, which is running a nonlinear multi-degree of freedom shear model in OpenSEES. So we'll go ahead and select that. So we have went through the introduction video, through the basics, or very quickly on the basic fields inside this interface. But right now we are going to go a little bit detailed. What is the procedure to follow in order to define this multi-degree of freedom system? So the first step would be, again, it's based on the hierarchy that we see here, or the layout. So the first step would be to define the system properties. And we mentioned that this is a multi-degree of freedom system. So each story essentially has some kind of relation between the lateral force subjected at this story and the drift. So this is what we are trying to model here, this behavior. So in order to do that, again, you will need to define all the parameters of the multi-degree of freedom system inside a text, an Excel file that will be imported to EaRL over here. So if we go to the supporting documents, if we go to the template MDoF shear model over here, so again it has this Excel file, it has different sheets that you will need to fill out. So in this example that we are using, we have a 4-story building. So we'll need to provide the height of each story. And these values that we see here, these are actually in the same units as the units of the project. So in this case, I'm using imperial units, which means this will be in inches and kip for any forces. So right now I have the height of each story. This, for the load, I need to provide the load at each floor. So this is the gravity load in kip values. If you're using the SI units, then this will be in kilonewton. I also need to provide the mass at each floor. So this will be used to compute the period of the structure and of course to conduct dynamic analysis later on. Then the 4 remaining sheets, you will need to define just one of them depending on which type of system property you are going to be using. So if you are using the elastic system property at each story, then you will just need to define the elastic stiffness at each story. So this is the relation between the lateral force subjected at a given story and the relative drift in this story. If you are using bilinear, then you will need 3 parameters to define this model. You will need the elastic stiffness, the yield force, and the post-yield slope as a percentage of the elastic slope. So right here, for instance, I'm using 3% of Ke as the post-yield slope, or the strain hardening slope, whatever you call it. If you are using the IMK, the Ibarra-Medina-Cravinkler bilinear model, or the IMK peak-oriented model, so in this case, again, you will need the elastic stiffness, the yield force, the ratio between the maximum force to the yield force. You will need the residual force. You will need the plastic drift. You will need the post-capping plastic drift and the ultimate drift, all in units of inches. You will need the lambda and c parameters that define the rates of cyclic deterioration in strength and stiffness. And actually, these parameters can be found, the full definition can be found in the EaRL manual, and also in OpenSEES. If you check the IMK bilin material, you will see what each of those parameters mean graphically as well, and how to define them. The same thing for the peak oriented. Again, these are all similar parameters. Additional types of deteriorating nonlinear models are going to be added to EaRL in later updates. So now, for this example, I will just use bilinear, a simple bilinear model. I will stay with the parameters that I have here predefined in this sheet. Then all I need to do is to browse for the location of this sheet. Again, I had this on the desktop in the supporting document, and I will need to select it. So right now it says please wait, and then now it says export is okay, and this little light over here turns green, meaning that the exportation has been correct and data are organized correctly inside the Excel file. The next step would be to define the ground motion records that will be used to do the dynamic analysis procedure and obtain the dynamic response of the structure. For this, I will need to browse for the folder that contains this ground motion. Inside the supporting documents, again, you have a folder called ground motions FEMA far field, which actually this folder contains the 44 ground motion records for the far field set or suite of ground motions that are defined in FEMA P695, if you want to read more about those. But again, this is up to the user, that you can have any type of folder that contains any set of ground motions. Inside this one, as we mentioned, there are 44 different records. They are saved in a text file, essentially, whatever the extension is, but a text-based file. And inside each file, if I can open one of those, for instance, inside each file there is the data for the uh, the essentially the spectral the ground motion acceleration history inside each of those files. In the same time, you will need to have inside this folder you will need to have another text file that need to be named all ground motion info, as we see here. And inside this text file it should have this type of information. So it has the ID of each, in the first column, the ID of each ground motion. The second column contains the names of each file or ground motion file, followed by the number of data points inside each file, followed by the delta t, which is the essentially the time between each recorded acceleration for the time history, for the acceleration history. So for instance, this is 0.01 second, 2,999 points at 0.01 second. So this means this ground motion is essentially about 30 seconds long, and so on. So you have this data, it needs to be organized in such way so that when you import this into EaRL, EaRL can understand what are the parameters associated with each ground motion, and analysis can be conducted correctly. So right now I will browse for this folder. So I will go to the supporting document, I will select this folder and say select folder. So now it says OK, and again this button turns green. This means the import process went correctly, and you can see here that automatically it says 44 ground motion records. But essentially when you do the analysis, you don't need to actually run the full 44. Maybe you just need to run a subset of these ground motion. So for instance, just for the sake of this example, I will just run 12 ground motion records, just a subset, so that we can run it quickly. Following, you will need to specify the analysis type. Essentially, you can do three types of analysis. You can do an incremental dynamic analysis on these records, which will take a bit of time, but you can do that. Or you can do simple scaling, so essentially scaling all these ground motions up to a given target intensity measure magnitude, or using a target scale factor. So if you use, for instance, target scale factor, then you will need to specify the scaling period and the scale factor that you are going to use. If you use a target IM, then you will need to provide the again the scaling period and the target IM, or the target spectral acceleration at this period. So now I need to scale to a given intensity measure, but I don't know what scaling period that I should do here. So I can run click on this button like get period, and this will run essentially a quick eigenvalue analysis, and it will provide me with the period of the structure, so of the multi-degree of freedom shear model. So if I click on that, so it ran this analysis, and it tells me that your definition here, this is actually has a period of 0.9 seconds. So here I will actually use 0.9 seconds to scale the target spectral acceleration at 0.9 seconds. I will, let's say, 0.75 g. For the damping, I will use 3%. And now with everything defined, I can start running my analysis. So you can see here, it will tell you using this status bar and the progress bar. You can see that it's running now ground motion number 3 out of 12 that you specified over here. So it takes around probably like from 3 to 5 seconds per ground motion. so which is reasonably fast. So right now at ground motion number 8. After this has been finished, after it finishes this, those two buttons for plotting the EDPs and saving the data to Excel will become enabled, and this will essentially let us look at the analysis results and see how does the multi-degree of freedom system actually respond. So we can see that it ran in 60 seconds, like exactly 1 minute for 12 ground motion records. If you click on plot EDPs, so we can see here the basic data that are being generated by this analysis. So the story drift ratio, the lateral residual drift ratio, and the peak floor acceleration. So we can see here, for instance, at the first story, we have a drift of around 2%, and this is the median profile in red. And then you have in gray lines the individual response for each of the 12 ground motion records. If you click on Save to Excel, you can select any directory, and all this data that you see here will be saved into an Excel file, because maybe you want to take this data and maybe modify something in it, amplify it, scale it, adjust something. So this you can do, and after you do that, you can actually re-import the data using any of the other import options in EaRL. So this looks fine, it seems fine, so I will close this. So now that everything is done, I don't need to do anything except just closing the window. And now if I go to the main module, so right now I see again it's green, so this means it's well defined, and it says here multi-degree of freedom model. So this is means that our definition is correct. You can check more by clicking on the scope to check that everything is correctly defined. So by clicking on the scope, actually if you scroll down to the response data, so we see that this is the multi-degree of freedom shear model, bilinear behavior. You can see the Excel file name that we imported with the properties, the ground motion folder name. You can see the number of ground motion we analyzed, the analysis type that we did, the target intensity that we scaled to, the scaling period, and the damping. So that's it. This is the way to define the response data, and again everything else with the project definition is the same. You can proceed with the computation of your analysis. In the later video, we will going to look at the FEMA P58 simplified analysis method, which is a very similar procedure to the one we discussed today. Thank you.